Hi everyone! In this video, we will discuss about the simplex algorithm. First of all, let's look at the LP problem. For question A, the question asks to solve the LP problem. For step 1, we need to convert the LP to a standard form. Before we convert, we need to make sure that there is no constraint with negative right hand side. Unfortunately, one of the constraints, which is constraint number 2, has a negative right hand side. Therefore, we need to multiply both sides with negative 1 to get a positive right hand side. So, we get a new constraint, which is this form. So, this is the standard form of LP problem. As we can see, for constraint 1, we minus E1 because the sign is greater than or equal to. For constraint 2, we add S2 because the sign is less than or equal to. Next, step 2. Convert to W form. Let's look at the constraint 1. There is no basic variable, so we need to add an artificial variable as A1. Because the LP is to minimize Z, then we minus MA1 to the objective function. Based on the W form, we know that the A1 and S2 is a basic variable, while X1, X2, E1 is a non-basic variable. Next step, we construct an initial W by referring a W form. We need to remember that all basic variables must have 0 coefficient in row 0, but in initial W, the coefficient of A1 in row 0 is negative M. Therefore, we need to eliminate A1 in row 0 by replacing row 0 with row 0 plus M row 1 to get the new row 0. Update the initial W with a new row 0. To determine whether the objective function is optimal or not, check the coefficient in row 0. For minimum problem, we need to make sure that the coefficient in row 0 is non-positive. As we can see, the coefficient of X1 in row 0 is the most positive. So, we choose X1 as an entering variable. Since we have entering variable, we use a ratio test. The basic variable with the smallest non-negative ratio will be chosen as a leaving variable, which is A1. Since we have entering and leaving variable, we proceed to the next step, W1. We need to change the coefficient of X1 in row 0 from 2 to 1. So, the ERO is 1 over 2 R1. So, we get the new row 1. Next, the coefficient in X1 in row 2 need to be 0. And the ERO is R2 plus R1. Lastly, the coefficient of X1 in row 0 also need to be 0, and the ERO will be like this. So, we get the new row 0. Now, we check the optimality condition. From W1, we know that there is no non-negative coefficient in row 0. Thus, we can conclude that W1 is an optimal W. Since there is no non-basic variable has zero coefficient in row 0, thus the LP has a unique solution. The optimal solution is x1 equal to 2, x2 equal to 0, and the optimal value is z equal to 4.
So, proceed to the next question. We need to find the dual LP for this problem. But, first thing first, before we convert the problem into dual LP, we must make sure that the value of right hand side are non-negative. And unfortunately, we detect that there is a negative value at the second constraint. So, what should we do now? Firstly, we must modify and change this value into positive first, so then we can continue to convert it into dual LP. So, this is the LP that I already modified. I got the positive 1 value here because I divide the negative 1 with the negative 1. And if you guys notice, the sign for the second constraint are also changed, which is from the greater to the less than. It is changed because I divide the whole second constraint with the negative 1. So now let's check it back whether there is a negative right hand side or not. So there is no more negative right hand side, right? So we can continue to convert it into dual. But before we convert it, we must know the rules. Rule number 1. The number of variables in primal here and here will equal to the number of constraints in dual. Second, the number of constraints 1 and 2 in the primal will be the number of variables in dual. Third, the value of right hand side at the constraint is equal to the coefficient of objective function in dual. Fourth, the coefficient of objective function from the primal are equal to the right hand side of the dual. And lastly, if the primal have a minimum problem, so the dual will have the maximum problem. So this is the dual LP that I already made. Okay, let's check it together. The number of variable is 2 because the number of constraint is 2. The number of constraint is 2 because the number of variable is 2. And the right hand side here are obtained from the objective function. And the objective function value here are obtained from the right hand side. Okay, next let's check the sign. The sign here are obtained from the sign restriction in primal LP. If this is the normal condition, so for the normal maximum, the sign will be less than. And sign restriction here are obtained from these signs. Okay, as we can see here, for the minimum problem, the normal is greater than. But if it is not normal, the sign will be less than. So here, y1 is greater than 0, which is normal because this sign is greater than. y2 is less than 0 because this sign is not normal. So this is how we obtain it. Alright, so now we proceed to the last question, which is we must find the dual solution for each of the LP based on their optimal tableau. Okay, so this is the optimal tableau that we obtained from part A question. Okay, firstly, how can we find the dual solution? First step is we must convert the primal LP which is this one, into the standard form. I already made the standard form for you guys. Okay, this is the standard form. Why did we minus E1 here? We minus E1 because the sign here is greater than and equal to. And we plus S2 here because the sign here is less than and equal to. And the sign restriction is as usual referred to the variable here. And the dual LP, I got it from what we just do just now. Okay, I copied and I paste it back here. Okay, now we can proceed to how to find the dual solution. We must find the solution for y1, y2 and w. I already list it here. Okay, how to find it? We can find the solution for y1 based on the coefficient of E1 in optimal row 0 of the primal. Okay, this is the row 0. Okay, E1. The coefficient of E1 is negative 1. So, the solution for y1 is negative in bracket coefficient of E1 in row 0 of primal. And why it is negative here? It is negative here because at the standard form the E1 is minus, right? So we just copied and substitute the coefficient of E1 and we got the solution is positive 1. Same goes to y2. Y2 is the coefficient of S2 in optimal row 0 of the primal. S2, the coefficient of S2 is 0. So, the solution is equal to 0, 2. And W, what is the solution for W? W solution is equal to the value of Z, which is 4. So, the solution for W is 4. That's it. This is how we can obtain the dual solution for this LP.
We want to show to you how to solve the LP problem using the LP Solve IDE. First, we just click the LP Solve IDE.
For the objective function, the mean is 2x1 plus 3x2. For the variable bounds, first constraint is 2x1 plus x2 more than and equal to 4. For the second constraint is x1 minus x2 more than and equal to negative 1.
After we type of the objective function and the variable bounds, so we must click the button solve to solve it, and the result we got z equal to 4, x1 equal to 2, x2 equal to 0. From this result, we know that x1 is the basic variable and x2 is non-basic variable. The constraint, row 1 equal to 4 and row 2 equal to 2. So that is from us. Thank you.